So the first speaker of the year will be Pedro Fernandes. He's actually an alumni of technical, so he did the bachelor and master area, but then moved to London to Queen Mary to do his PhD, and then had a couple of postdocs. So one in Nottingham, then moved to the University of Southern Denmark in Odense, and now he moved to Heidelberg University with, although I think it's the same group, right? They just moved from Denmark to Heidelberg. And he's gonna tell us about how you can break the black hole uniqueness at supermassive scales.
So hi everyone. Thank you for having me here. As Richard said, I did my bachelor's and my master's here, and so it's absolutely insane for me to be presenting here. And if someone told me, "Oh, someday you'll be presenting as a researcher in technical," I'll be like, "Yeah, that's amazing. Where do I sign up for that?" It's really amazing to be here. So today, I will be telling you about this work, breaking black hole uniqueness at supermassive scales. I did this work with Astrid Ashmorn, Ahorn Held, and Hector Silva. And I will not try to solve any of the problems of GR or anything like that. This paper, I want to think of this paper as a proof of concept of why we need experiments targeting all black holes at all mass scales, and not just a certain mass scale of black holes. And this comes from a sequence of talks that I heard, and my collaborators as well, where people essentially said, okay, we expect higher energy modifications to gravity, smaller black holes have higher curvature, and so we expect that solar mass black holes or smaller black holes are better tests of general relativity than supermassive ones. And there are a class of people who, based on these arguments, just dismiss experiments such as the Event Horizon Telescope, and they will say that, okay, the Event Horizon Telescope is just there to learn about astrophysics, not about the nature of gravity. And so this work is a proof of concept that this might not actually be true, and we can actually have black holes, new physics at supermassive scales. Sorry, so this is not working now. Okay, perfect. Okay, and I will start this talk with a brief description of the Kerr metric, which is a solution of the Einstein field equations, and it describes a rotating black hole. Now, this metric is extremely simple. Black holes described by the Kerr metric are described essentially by only two microscopic parameters: the mass of the black hole and its spin. And the Kerr metric is special in that it is not just a black hole solution of the Einstein field equations, but rather it is the black hole solution to the Einstein field equations. And so the Kerr metric is unique in this sense, as proved by Carter and Robinson in the 70s. And so general relativity has a very sharp prediction, which is all vacuum black holes scattered all through the universe are described exactly by the Kerr metric. This is a prediction of general relativity. And so this is an astounding thing to say, because we are essentially saying that the same theoretical model will describe objects that range at least 10 orders of magnitude in mass, from solar mass black holes to black holes of about 10 to the 10 solar masses, where we have observational evidence for their existence. This is absolutely crazy. The same theoretical model describing things ranging 10 order of magnitudes in mass. At the same time that GR makes this very sharp prediction, it also paves the way on a way to search for new physics, because any potential deviation that we observe from Kerr would be a signal that there is new physics. Now, do we have any reasons to believe that there is new physics? And we have a ton of new reasons to believe that there's new physics. I won't go into details in any of them. I'll just maybe list a few of them. For example, we don't have a fully consistent theory of quantum gravity. GR predicts its demise in the center of black holes, where the theory breaks down near the singularity. We don't fully know about the nature of dark energy and dark matter. And right now, in recent years, we've had a couple of cosmological tensions, such as the H0 tension, which is now at 5 sigma or above 5 sigma. And so we have reasons to believe that there's new physics in the gravitational sector. And within the gravitational sector, where can we potentially observe new physics? And I pose this question because GR is very well tested in the weak field regime at solar system scales. And so since we've tested the theory so well in this regime, we don't expect to see any new physics there. However, we are probing now new regimes. We are probing the cosmological regime, cosmological scales, and we are also recently we have started recently to probe the strong gravity regime. I will focus on this talk in the strong gravity regime. And now, if we want to observe new physics, they should only manifest in these regimes, because as I said, we've already tested GR very well in the other regimes. However, if we try to come up with a new theory that modifies gravity, it most likely will conflict with observations that we already have. And so finding a new theory of gravity, a new alternative theory of gravity that is compatible with all our current observations is highly non-trivial. Now, people are smart, physicists are smart, and they come up with ideas. And some people came up with this idea, this mechanism called scalarization. And this is a mechanism that I will just try to explain briefly how it works, and is a mechanism essentially that shields new physics in low curvature regimes, such as in the solar system and the regimes we've probed very well. However, with this mechanism, new physics would be manifest at strong curvature scales. And none that I will present in this section is new. I will just do a brief review of this mechanism of scalarization. So, as I said, one way to excite new physics exclusively in the strong gravity regime is scalarization. And in scalarization, for scalarization to occur, for this mechanism to occur, you need two ingredients. You need at least one new scalar degree of freedom in your gravitational theory. And the theory should allow for at least two branches of solutions. So you should have a branch of solutions which coincides with the GR solutions. And so you can have a weak field regime described by GR, as usual. And you can have another branch of solutions, so some solutions that differ completely from those of GR, that are excited exclusively in some regime. And the way scalarization works in most models is through a tachyonic instability that I will now proceed to explain, or try to explain with a very simple model, which I will try to do this with the 1 + 1 dimensional wave equation, where we have some scalar, which has the usual wave equation, and we have a mass for the scalar. Now, if the scalar is massive, we can describe the field in terms of plane waves, as shown here. If you solve this differential equation, you get a solution like a plane wave, where we have this dispersion relation. Something occurs when the mass of the scalar is imaginary, so when mu squared is negative. In this case, for small wave number k, you actually have a negative number inside the square root. And so you get that your plane wave solution is not actually a plane wave, but it's actually an exponentially growing mode. And this signals an instability. So if you have an imaginary mass, you'll have issues, you'll have instabilities in your system. Pictorically, this can also be explained by looking at the potential of the scalar. So this is the usual potential for a massive scalar, and where the mass is positive. Now, if the mass is imaginary, the potential will flip, and the scalar that's used to sit at the bottom of the potential at the minimum will now sit at the top of the potential, and it will be unstable. It will tend to roll down the potential. And this is the idea. If you have a tachyonic instability, you'll run down the potential. However, there are some mechanisms that can cure this instability. And one way of doing this is by inserting nonlinearities in your system. For example, this is the Higgs. If you insert nonlinearities in your system, which in this case would be a quartic coupling, the potential will not run down all the way to infinity anymore, but the nonlinearities will create a new minimum somewhere in field space, and you can actually have a new scalarized configuration. So whereas before you had a scalar-free configuration, now the tachyonic instability will drive you to a scalarized configuration. And this is very much in analogy with the Higgs mechanism. Now, let's extend this very simple pictorial example to curved spacetime, and we will assume that we have a new theory that contains a new scalar field, a new degree of freedom, and the scalar field obeys a Klein-Gordon equation as usual, but now we don't have a constant mass for the scalar. We have some effective mass that will depend on the space-time point x. And I will show you in a couple of slides on how to do this. Now, let's suppose the following situation. Assume that near a very compact object, such as a black hole or a neutron star, the effective mass is such that it becomes negative near the compact object. Now, in this situation, the scalar would become a tachyon near the compact object, and it would induce an instability near that object. And in all other regimes, far away from a compact object, we would have an effective mass which is positive or not negative enough to cause an instability. And this is the idea of scalarization. So now the simplest model of black hole scalarization is given by this class of theories, which are called scalar Gauss-Bonnet theories, where a lot of people have been working on these type of theories in the last few years, where these theories are a subset of scalar tensor theories, of Horndeski theories, where we have, in addition to GR, we have a new scalar. The scalar can have a mass, or more generally can have any potential you want. But the essential feature here is we have a coupling between the scalar and this term here, which is called the Gauss-Bonnet. The Gauss-Bonnet is this combination of curvature. It's quadratic in the curvature, and it has really nice properties. One of the really nice properties of the Gauss-Bonnet term is that you can add it to a four-dimensional action, you can couple it to a scalar, and your field equations will remain of second order. So it will not introduce any other degrees of freedom. You will not have Ostrogradski instabilities. This is the nice property of the Gauss-Bonnet, and that's why I use the Gauss-Bonnet and not any other curvature invariant. Now, if you vary your action with respect to the scalar field,
This, as a principle of, or would you symmetries as principle, why do I couple with R squared terms and not with R? Not with the linear terms in curvature?
You can couple with a linear term in the curvature, but yeah, that term can be there, but it will not have any relevance for this talk because this talk concerns black holes. And the coupling between the scalar and the Ricci scalar will introduce a mass proportional to the Ricci scalar there, but for a black hole, or at least for a Schwarzschild black hole.
You're locally a very high curvature, you want only quadratic. I mean,
Yeah,
you look on,
I want something which is not vanishing, which is the case for the Ricci scalar,
yeah, okay,
because
sorry.
a Schwarzschild black hole has a zero Ricci scalar, and it will not affect the scalarization mechanism. So yeah, you can have all those linear couplings between the scalar and the Ricci scalar, the scalar field and the Ricci scalar, but they will not impact what I'm telling you about right now. Okay? And yeah, by the way, at any point, if you want to ask me any questions, please interrupt me and ask me, okay? Okay, so as I was saying, if you take your action and you vary your action with respect to the scalar fields, you will get a Klein-Gordon equation of the form that I showed you before, where now you, instead of having a constant mass, you have an effective mass, which depends on the space-time point because you have this dependency on the Gauss-Bonnet term. The Gauss-Bonnet term is not constant across space-time. For example, for a Schwarzschild black hole, it's non-vanishing, and it's non-trivial. And so the effective mass of the scalar depends on the space-time point. Now, if you take a careful look at all the field equations of this theory here, you will find that phi equals 0, so a constant scalar profile, together with any GR solution, is a solution of the equations of motion. But the crucial point here is that besides the GR solutions, you also have other types of solutions. You have scalarized solutions, as I will show you later. Now, exactly. So the Gauss-Bonnet curvature, the Gauss-Bonnet invariant for Schwarzschild spacetime is given by this expression here, which is quite familiar because this is how we see that as a curvature singularity at r equals 0 for Schwarzschild, for example. And we can see that the smaller the black hole is, the larger the curvature in its vicinity is. So, for example, the Gauss-Bonnet curvature in the horizon of a Schwarzschild black hole is proportional to 1 over m to the 4. So the smaller the mass of the black hole, the larger the curvature is. And so if any Schwarzschild black hole we consider is small enough in this theory, it will happen that this quantity here might actually become negative. And in that regime, we will excite a tachyon. We'll have a tachyonic instability. And so in this situation, you can do perturbation theory. You can do all sorts of complicated analysis, and you'll get to the conclusion that if the mass is of the order of this coupling here, this which appears in the action, this coupling here, alpha, if the mass and the coupling have the same length scale, more precisely, if this relation is obeyed, then you have a new branch of black holes. So black hole uniqueness is lost. You will not have only the Schwarzschild black hole, but you'll have the Schwarzschild black hole, which is unstable in this regime, and you'll have a new branch of solutions, which are called the scalarized solutions. And these are just some plots showing you some physical properties of the scalarized solutions. For example, here I am plotting the scalar charge, which is a kind of charge related to the scalar field, which is potentially detectable in binaries. And we see that there is an interesting behavior here because you have a non-vanishing charge. And here I plot the entropy of the scalarized black hole in comparison with the entropy of a Schwarzschild black hole. And we observe that the entropy of a scalarized solution is always greater than that of a Schwarzschild black hole. And this means that it is entropically favored, which has some loose correlation with being the dynamically preferred solution. Okay, so this coupling constant alpha will define the scale at which there is new physics. It will define the scale at which we observe new black holes. And how large can this alpha be? Which black holes, which mass ranges of black holes can scalarize? And the answer is that this alpha cannot be arbitrarily large. And the reason is that we have really good observations, for example, of neutron stars. And neutron stars are also highly compact objects. And these neutron stars will also be susceptible to this scalarization mechanism. However, the pulsar data, the binary pulsar data we have is in very good agreement with GR. And so we don't want neutron stars to be very much scalarized. And so taking into account all of these factors, these people have done analysis on data that we have, and the scale where we can have new physics is of at most kilometers, which translated to solar masses is about 1 solar mass. So this scalarization mechanism, if it is to be compatible with observational constraints, can only, given current observational data, show up in solar mass black holes. Yeah.
So on this scalarization, where would the energy come from? You create particles, right?
Yes.
Okay.
Yeah.
Energy must be.
So this is a dynamical process. So you have a stationary black hole that's just sitting there, and at some point, because it is formed with a small mass or because dynamically via Hawking evaporation, whatever, it is in the instability regime. It becomes unstable. And what happens dynamically is that during this dynamical process, the black hole will emit gravitational waves. Some of the mass of the black hole will be transferred into a scalar cloud, and the scalar field will grow. And you will settle in an equilibrium configuration, which is a black hole with a smaller mass and with a scalar field profile. That's the idea.
Okay. So, but that would, so you're saying there would be more, so somehow there's more energy extracted than just from Hawking radiation process.
Yeah, Hawking radiation plays no role in here.
Yeah, okay.
You just need a black hole
Maybe-
to reach small.
Yeah, but you need a little perturbation in this application. It could be Hawking radiation.
Yeah, fields fluctuate. Yeah, in general, if this is a field in nature, it will fluctuate. And
But I think really classical, how does it square with the concept of irreducible mass? How does it square with the concept of irreducible mass?
It's not pure GR.
But then how does it get modified?
I mean, you're not breaking thermodynamics, right? Entropy is higher for the solution.
the solutions will still have an entropy. It will be different from the Bekenstein-Hawking entropy, but it will still have an entropy. Yeah.
So, and then what is the maximum entropy state?
Uh,
So would you take all the energy from the black hole and that would be your maximum entropy state, or some equilibrium where you still have black hole and the scalar?
So these black holes, at some point. So what's your question? Sorry, can you repeat the
So
question?
the system wants to go to equilibrium. So the maximum entropy.
Yeah.
So where do you find maximum entropy?
In what sense? I mean,
So would
you have some.
would all the energy from the black hole kind of go into the scalar particles?
No, I wouldn't say that all the entropy of the black hole goes into the scalar particles.
The energy mass.
Yeah, you have some energy stored in the scalar field profile for sure.
Yeah, but there's some equilibrium where you
Yeah.
still have a black hole and the scalar cloud.
Yes, yeah, exactly, yeah. Yeah. So what's the question? Sorry.
And if that comes that, sorry, that corresponds to the maximum entropy that would be there.
Yeah.
Right. So, right. Okay. Yeah, I would say so. Yeah. I mean, systems will evolve in the direction of maximum entropy, and
But I think, if I may, sorry.
yeah.
I think one point is also the instability at some point changes because you're changing the coupling with the scalar Gauss planator, with the Gauss planator term, right? The Gauss planator term changes, so the non-linearities during the evolution will kind of saturate, make the instability saturate. I think that's the point. I think that's what happened, I believe.
Yeah.
And there are some numericals that show that, for example, collapse of scale naturally. If the mass is in the region of parallelism naturally, then this solution is not going to anything else. It's like a thing
Okay. Okay, I'll get going because apparently I'm short-ish on time. Where was I? Okay. So I was just saying that. So let's do a summary. So there's this mechanism called scalarization, where we can have things different from GR, different dynamics from GR in the strong field regime, but in the weak field regime, everything remains the same. And this would happen for solar mass black holes. And this is in good agreement with that general expectation that I told you about in the introductory slide, that most people expect new physics to show up at high curvatures and therefore for small black holes rather than larger black holes. Now I'm going into the main part of this talk, breaking black hole uniqueness as supermassive scales. And so let me just define very briefly what it is I mean by supermassive scales. And by supermassive scales, I mean any black hole with a mass greater than about 10 to the 5 solar masses, which are the black holes we expect to sit in the center of galaxies. Now, again, there's this common expectation that the higher the curvature, the more likely we are to see new physics. And supermassive black holes, if you do your calculation, they have very small horizon curvature. And so intuitively, this would mean that supermassive black holes are not very prone to new physics. They are just very classical objects, not sensitive to any modified gravity. And also one of the mathematically, one of the reasons is that if you have a new coupling in your theory with a length scale L, and you have some black hole with mass M, new physics effects will scale like this. And if by observations we have that this should be solar mass and this is supermassive, this is very small. And so any effect on your geometry will be very small. And so supermassive black holes are very generically expected to be described by the Kerr metric to very, very good high accuracy. And this would mean that experiments such as the Event Horizon Telescope that probe supermassive black holes would not see any deviation from GR, would just be there to probe astrophysics. And the same would be said for at least some mass range of the LISA experiment. Now, what I will try to do is to use the scalarization mechanism and tweak it such that solar mass black holes and neutron stars and all of those small objects remain described by GR, but instead I have new physics for supermassive black holes. And the idea is to take the way the Klein-Gordon equation as before, but now I will tweak this effective mass such that it is sufficiently negative around supermassive black holes, but positive or maybe negative, but not negative enough to cause an instability in all other regimes. And now, so essentially, this was the idea me and my collaborators had, and we spent like 3, 4, 5 months looking for a way to implement this, and we didn't get anywhere. At some point, we got to the answer, and in like a week and a half, the paper was written. So it's one of those situations where you spend months trying to find something, and then you find it. Everything just flows from there. And the thing we did was just to consider the most simple generalization of the effective mass that you can, and which is to add a quadratic term here, a quadratic Gauss-Bonnet term here. So, sorry, the labels are very small, but here is effective mass squared, and here is curvature. So if you plot effective mass as a function of curvature, you will get something like this.
But
Now,
if you, sorry,
yep.
but if you couple to quadratic Gauss-Bonnet, will you still get second order equations?
No, I will come into that in a minute. Let's just now assume this, and I will go into that question in a few slides. So now, if we look at the profile for the effective mass, you have this. And you observe that for very high curvatures, for example, solar mass black holes, the effective mass is positive, and there can be no instability. Now, if you go to some intermediate curvature regime, you have a negative effective mass, which is quite negative, very negative, and can cause an instability. And if the curvature is very, 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 very small, you'll just get to a point where the effective mass is negative, but not negative enough to cause an instability in curved space. So if we take that Klein-Gordon equation here with this effective mass, we perturb a Schwarzschild black hole, do all the calculations correctly. These are just some details that don't really matter. If you do this calculation, you'll get a region of parameter space where on the y-axis I have the black hole mass in units of this coupling here, where this is just the usual scalarization coupling, and alpha 2 is a new coupling I've added. Here I have the black hole mass, and here I have the ratio of the two couplings. Now, when I don't have the new coupling, this is the usual scalarization scenario where below a certain mass, all Schwarzschild black holes are unstable. However, once I turn on the new coupling I've added to my theory, I will have an instability region which is bounded from above and from below, where the Schwarzschild black hole is unstable. And this is the region where scalarization can occur. And so we see that if we take the mass, if we take the coupling, this coupling alpha 1, to be on supermassive scales, and so the black hole mass would be here on supermassive scales in this region, and the couplings are of more or less the same order, supermassive black holes would scalarize if they are in this mass region, whereas solar mass black holes would be in this region and they would not scalarize. And so we can have a region of parameter space where supermassive black holes are different from GR, but solar mass black holes are not. Here. Yeah, so neutron stars are the problem with the original scalarization model and taking the coupling to be very large. So what happens here with neutron stars? Neutron stars are, as I said, very compact. They have very high curvature. And intuitively, if we look at the plot here, they have very high curvature, so the effective mass will be in this area. And if we do the analysis more carefully, if we look at the potential for perturbations of the scalar around the neutron star, we see that the effective potential that controls the scalar perturbation is not negative enough, which is, so this blue line here is the usual scalarization case, where we have a very negative region that will cause an instability. But once we turn on the new coupling, we get to a point where we don't have a negative region and neutron stars don't scalarize anymore. And so we can have solar mass black holes and neutron stars all described by GR, and supermassive black holes which are not described by GR. Okay, so far I have only considered this modified Klein-Gordon equation. What is a reasonable model that can produce such an equation? And the simplest model that can give this is just to add this quadratic Gauss-Bonnet term here. And I got a question, which is, okay, so if you add this term here to your action, don't you have high order field equations? That's true, we have. But this is a situation very similar to f of r gravity, which some of you might be familiar with, which is because of the really nice properties of the Gauss-Bonnet term, we can rewrite this theory here, at least this red bit here, as this, where we have a new scalar degree of freedom. So we have phi and we have psi. And on shell, these two theories are equivalent to each other. Because if you use the equation of motion for psi, you'll get that psi is just essentially proportional to the Gauss-Bonnet. And when you substitute it in the other field equations, you get the same field equations as you have in this theory. So in a nutshell, indeed, there are high order equations of motion here, which hide a degree of freedom, but it's just a simple scalar degree of freedom with second order equations of motion. And so it's not an Ostrogradsky ghost. And so we don't have any issue with Ostrogradsky ghosts. Okay. So yeah, we have this model, which reproduces exactly the Klein-Gordon equation that scalarizes supermassive black holes. We don't have any issues with Ostrogradsky instabilities. And we have solved the field equations of this theory here. And what we observe is in very good agreement with perturbation theory, where in this red region, we have a region where black holes are different from GR. And so this can be taken at supermassive scales, and they can have properties which differ a lot from those of the GR black holes, as seen, for example, in the entropy or in the area, which in these plots are compared. We compared the entropy and the area of the scalarized black hole with that of the GR black hole. And we observed deviations of about, 0.91. So very high deviations. Now, just a quick side note before I finish, which is on the cosmological stability of the theory. So if we have a theory of gravity, we can't just blindly look at either black holes or cosmology. The same theory should give rise to a consistent evolution of the universe and consistent observations of black holes. And this is something which doesn't usually happen in the usual models for scalarization, where the effective mass of the scalar becomes very negative during the inflationary period. And these people have studied this issue, and they find that as a catastrophic instability during the inflationary stage of the universe. And this would prevent inflation from occurring, at least in the amounts we need. And we wouldn't have the cosmological evolution that led us to here today. Now, in our case, once we add this coupling here will dominate during inflation, where curvature is very high. and this contribution is always positive. And so we will not have any instability during inflation. Inflation will occur just as in GR, and we'll have a lambda CDM like evolution all through the course of the universe. And so it is compatible with all constraints that we currently have. So in summary, I have introduced a new model of scalarization where new physics is manifest not for solar mass black holes or neutron stars, but contrarily to common intuition, new physics is manifest on supermassive black holes. And so this is a proof of concept. I don't believe this is the ultimate theory, but it is a proof of concept that there are theories out there where we can have everything compatible with current observations, and where supermassive black holes differ a lot from GR. And so to really probe all of gravity, to really test the theories of gravity we have in GR, we need to test also, we need experiments targeting supermassive black holes. We need the Event Horizon Telescope. We need LISA to target these supermassive scales. And
Sorry, what
Yeah.
was the argument why you need supermassive black holes? I mean, on the
For what?
supermassive
Sorry.
black hole, on the surface of the supermassive black hole isn't, so I would think the curvature is not as high, because as you say, the curvature is.
Yeah,
black hole,
it's small, yeah. for a supermassive black hole, yeah.
So, and I would assume that's also true for the Gauss-Bonnet. zone, that
Yeah,
it's
so,
also
yeah.
Small, no, it's large for small black holes.
Yeah, the Gauss-Bonnet is large for small black holes, yeah.
So doesn't that mean?
You've seen the
Ah.
quadratic
But
curve now.
yeah,
Okay,
exactly.
I
So
see.
it all goes back to this curve here. So if you have a large curvature, you don't have any instabilities. You just have GR. That's the point. Yeah. Yeah. So I think this is more or less what I wanted to say. And there's some ongoing work with me and collaborators, the same collaborators, where since these observations would target, this theory would affect supermassive black holes, we are looking into the shadows and observational images of these black holes, how they would look like if they were to be realized in nature and at the center of our galaxy or some other galaxy. And in red, we have what is called the lensing band, which is an image property of black holes. And in red, we have the image property, this property for a scalarized black hole, and in black is for Schwarzschild. And in this direction, I'm increasing the coupling, and the same here. And I see that as I increase the coupling, the red property, the red lensing band, will differ more and more from GR. And at some point, the coupling is so large that it differs a lot, and we should be able to constrain this theory. Or on the other side, if we have more accurate observations from the Event Horizon Telescope, for example, and we see something that deviates from GR, perhaps we could explain with a model like this or some other thing. But this is a candidate for this. Yeah, that's all I wanted to say. Thank you for your attention. On time?
Yeah, perfect. Yes. So you have plenty of time for questions. So, David.
Yep.
I have sort of two questions. So you showed the slide where you said we computed solutions numerically and spherically. My first question is, what did you actually do there? Like, did you assume that things were static and then try and solve the equations, or are those results from a time evolution?
No.
And second, when I look at those two curves that you have in that slide, they agree pretty well, but not everywhere, right?
Yeah.
So in the region where they don't agree, is that an indication that there's a lot of numerical error, or is it physical? Or like what's the cause of that?
Okay, so first of all, to the first question, we assumed static metric, spherical symmetry, and just solved those field equations. We didn't do any time evolution. So we just looked for like a Schwarzschild solution, like a static and spherical symmetric solution, and solved those elliptic-like equations. Then, yeah, there is a region where there is not a perfect agreement between the two curves. So we have checked our code thoroughly. We did all convergence tests, all of that, and we observed really nice convergence properties, agreement,
So even in the
smaller.
regime where the theoretical seem
Even
to
when-
disagree.
Yeah, even when they don't agree. So we
So
we
why?
think this. We don't know. We think this is something physical, and this would mean that, for example, black holes here would be unstable. Schwarz black holes here would be unstable, and there is no scalarized solution, at least no static and spherical symmetric black hole solution. Our
Sorry, but doesn't the theoretical prediction say that there should be? So,
there should be something
so
else.
there's really a contradiction between them.
Not necessarily, because we just looked for static and spherically symmetric black holes. It's possible, and this has happened in other models of scalarization, where there are static, non-spherically symmetric black holes, but axially symmetric black holes, which are static.
You can't get this
Which I-
spherical by assumption.
Exactly. So this is also an interesting avenue for future research, which is to look for solutions which are not spherically symmetric, which is what we think might be going on here in this regime. In this regime, there's a region where both Schwarzschild and scalarized solutions exist. It might be that maybe the scalarized solution here is unstable. We haven't looked at stability of the scalarized solutions yet. This is something also on our radar.
Probably is a silly doubt, but so in general, when I take higher curvature term, I will get an extra degree of freedom. Gauss-Bonnet here should be the only one, the quadratic in curvature that doesn't give an extra degree of freedom. Why is this true even when I couple it with another scalar? Is it obvious? Is it real? I'm not sure.
Okay, so I think the idea is the contribution of the Gauss-Bonnet term to the field equations will be something like, I'll just write the indices. Then you have some covariant derivatives here, and with correct indices here, I'm not checking. And you have function of whatever scalars you have here, phi1, phi2, whatever. This is the term that the Gauss-Bonnet gives when you vary the field equations. So no matter how many scalars you couple to the Gauss-Bonnet, you just have second order field equations. All the metric parts are here. And this is how the Gauss-Bonnet differs from the other curvature invariants. For other curvature invariants, you would have a curvature term which is inside the covariant derivatives, and you'd have higher order field equations. But for the Gauss-Bonnet, this is a special thing. Everything you can couple how many scalars you want, and you still get second order field equations.
So what about the weak field limit of the theory? Because if you put a length scale at 10 to the 6, it's quite large.
Yeah.
You can imagine that in the solar system, it's like scale.
Yeah, so that's an interesting point. So, for example, I think Sagittarius A star. I think I did this calculation at some point when I was working on this. Sagittarius A star, the black hole in the center of our galaxy, has a horizon curvature which is very close to the one we have here on Earth. However, we are not scalarized as far as I know. So we have this discussed in our paper, and we have some calculations. It all boils down to compactness. So a black hole is very compact, whereas the Earth or any other weak field object like the Sun, Mars, whatever you want, it has a compactness which is like 10 to the minus 9 or 10 to the minus 12 instead of a compactness which is 1 for a black hole. And compactness plays a role in the scalarization mechanism. If you do the calculations, you will see that the equations that govern the perturbations for the scalar, the tachyonic instability, are proportional to a factor of the compactness cubed, which for a black hole compactness cubed would just be 1 cubed, which is 1. But the effective potential that governs the perturbations would be suppressed by a factor of c cubed, which would be like 10 to the minus 9 all cubed, which is very small, 10 to the minus 27. And so we have a very small potential that governs the tachyonic instability, and it will not give rise to a tachyonic instability in the solar system or in the weak field regime.
But even if there is no tachyonic instability, it could modify the value of light.
No, so that's the point, because there is no tachyonic instability, and the field equations allow everything to be described by GR.
And so you don't couple it to matter.
No, the scale is not coupled to matter. But even if it was, the configuration that we observe in the solar system would be phi equals 0 and GR solution, which is allowed by the field equations, which is why this model passes solar system tests. So the geodesics that any matter would follow would just be the geodesics of a space-time, which is a solution to the Einstein equations.
Now that you're targeting supermassive black holes at the center of galaxies, like, have you thought of describing like matter with this, or like, I don't know, some rotation curve for galaxies or something with a scalarized black hole instead?
We thought about that, but I don't think it is possible, because even though the metric is modified with respect to GR, and we have supermassive black hole in this model, which is not Kerr, the fall off of this black hole, so the approximate metric of the approximate solution of this metric near spatial infinity, or at the edge of the galaxy, is Newtonian. And so we would recover exactly the same rotation curves as in GR.
So for scalarized solutions, you say you can still stars.
Yeah.
But those by the low
No, we haven't. It's something which is quite difficult to do numerically. Because there are, inside the horizon, you run into all sorts of problems if you have singularities. And even then you have Cauchy horizons and all. It can be done. It for sure can be done. It's a bit more difficult, and we haven't done it yet. But you're free to do it.
If you enjoyed the video, like and subscribe.